In an earlier section of this info book, we had talked about CMOS inverter circuits, and we modeled the P channel and the N channel CMOS transistors as perfect switches. So, as we do in engineering, sometimes we layer in extra parameters within our mental model. This is still an oversimplification, but one thing we could do is come up with a resistor network. All right, so we have this series loop. So you see the voltage source, the current coming this way. Here's resistance AP, P for the P channel. Here's resistance AN, N for the N channel. And the idea is we have a control input A that switches the values of the resistance. Okay, so in the ideal case, which is what I've shown here, in the ideal case, 0 ohms means that we have a short circuit. It's treated just like a wire. And infinite resistance would be like the open case of the transistors that we talked about before, where the resistance is infinite. Okay, so we can then switch. Notice with the input being low, we get an output that's high. And conversely, if we take the high input, switch A to be high, that flips the values of the resistances that we're modeling for the switches. Okay, so RAP would now be infinite. It'd be essentially an open circuit. And RAN would be 0, which would be the short circuit. And that forces the output to 0 volts. So things are working exactly like we talked about in the previous section of the book, where this acts like an inverter. And the role of RAP and RAN is the transistors that are implementing these switches. All right, so the next thing I wanted to talk about is in real life, these are transistor devices and they're not perfect. They don't have 0 resistance for short circuits. They don't have infinite resistance for open circuits. So again, it's layering an extra level of abstraction in here, or we're actually removing a level of abstraction where we can model what would happen if you had sort of a typical load. All right, so with a typical load, the resistance when the P-channel transistor is on would be still pretty high. Let's say it's 1 gigaohm, all right? And the low resistance would be, let's say, 1 kiloohm, all right? Kiloohm is a significant resistance, but compared to a gig, it's pretty negligible. All right, so what I've done here, and you don't need to know a lot of circuit theory to do this. This is one of the first things you learn in the first couple of weeks of a circuits course is this idea of a voltage divider. Okay, so you take this series loop of 2 resistances. You can calculate the output voltage that I have here by a voltage divider where we take RAN divided by the sum of the 2 resistances. And we see that in that particular case, it's not exactly 0, it's 5 microvolts, which is essentially 0. All right, the other thing that we did here is I calculated the power requirement that is being supplied by the power supply. That would be, according to circuit theory, Vs times I, and we know what I is. We can get that also from a voltage divider. Anyway, you don't need to know the circuit theory. It shows you that under typical conditions, there's still some leakage kind of currents. It's not infinite. There's a tiny leakage current. The static power is very small, but it's not 0. Okay, so if you had a whole lot of transistors in a circuit, that starts to add up to something that you don't neglect. All right, and so later in the course, we'll talk about how you can gate different parts of a circuit to improve the power efficiency of that circuit. Okay, but that's the basic idea. Now, I want you to flip through here. This graphic is available to you. When it's a low, all right, what happens with a low? Well, with a low, RAP is modeled as being a low resistance compared to 1 gig. So this looks like the short circuit. This looks like the open circuit. You do the circuit analysis. There's a voltage divider. You get the output to be 5. All right, so it's operating like we would expect, even under typical conditions, but we do have some leakage currents that result in some power loss. All right, so in the ideal case, no current flows at all. The typical case, there's small amounts. Now, another thing that could happen is you could operate in a condition where you don't give the transistor inputs really clean high voltages. It might drift down to the lower range or even outside of the noise margin ranges that you get for a transistor circuit. And so here is the degraded case where hopefully we wouldn't be operating like this, but it could be that when you flip the input A. All right, so we're gonna make that a low. It gives you a 1 kilo ohm P channel resistance, but the N channel resistance is not as large as we'd expect. So this is not fully off. Okay, it's not fully an open circuit. And because of the voltage divider, you actually get a drop on the output circuit. It's no longer 5, it's 4.5. The current goes way up and the power requirements go way up. All right, so you can see that happening under both conditions. If you don't get a really strong off, all right, and you have more leakage currents, then you could get, a voltage of about 0.5 volts instead of a 0, and you could get significantly more power consumption. All right, so this is not a perfect representation of what happens with the transistor. Transistors are more complicated devices, but I think it's better than just to looking at this in terms of ideal switches. All right, so we have a model that incorporates some real world aspect of this where there is leakage current involved.